Again, welcome to calculus. In these lectures, we're going to cover the derivative and the slope of a graph. So our main objective is to approximate the slopes of a tangent lines to graphs at points. We know in a linear or straight line, the slope is always constant. But with a nonlinear graph, the slope values can change at any point. It depends on the steepness of the curve. Next, we're going to use the limit definition to find the slope of graphs at points, and also use the limit definition to find the derivative of a function. So first, we start with the definition of calculus. Here we say calculus is a branch of mathematics that studies rates of change of a function. So we can say a calculus is a dynamic concept. And the goal of calculus is trying to study a phenomena within the rate of change. We can say in time, interval of time, from let's say T1 to T2, what is the changes? So far we have learned how a slope of a line indicates the rate at which the line rises or falls. And we know for a straight line, the slope is always constant at any point. But if we have a graph or nonlinear, then the rate at which a graph rises or falls change from point to point. And this is a good example here. For example, the slope at S1 and Y1 point is different from S2 and Y2 point, and also different from S3, Y3 point. Now, to determine the rate at which a graph rises or falls at a single point, we can find the slope of a tangent line at that point. So a good example here, a straight line that touches a nonlinear graph once is called a tangent line. So here we say from the geometry, we know that a line is tangent to a circle when the line intersects the circle at only one point, then it's tangent to the circle. And previously, the same example here, the straight line here, they are tangent to the graph because they touches the graph only once. And that's a few examples here, tangent lines to non-circular graph. So the line is tangent to the three graphs here because they touch the graph or intersect the graph only once. We're also going to have the second line, which we are going to get 2 points on the graph. So in this section, we will see how the notion of a limit can be used here. So what is the slope of a graph? Because the tangent line approximates the graph at a point, the problem of finding the slope of a graph at a point becomes one of the finding the slope of a tangent line at a point, at that very point. So we may have a graph, as we saw a previous example, 3 points. If the line is tangent to the point, that graph, then we can find the slope there. So example is given here. They say we should use the graph here to approximate the slope of a graph of f at s equal to s squared at the point 1, 1. So first of all, we plot our graph, f at s equal to s squared. Then we get our point on the graph when s is 1, y is 1. That's where we are looking for the slope. So here we draw our tangent line, and then we find the slope. Using the graph, you can see that when s increase once, y will increase twice. And we know slope is always the difference of y divided by the difference of x. So this means our answer will be again 2 minus 1, which will give us 2. So here we say the graph f at s equal to s squared, the point at 1, 1. So dy is 2, the change in y is 2, the change in s is 1. So 2 by 1 will give us 2, which means the slope value is 2. Next, we go to the slope and the limit process. Now we have to use this, what we call the second line. A second line is when you have a line on the graph and it touches it twice. So we can see we have our graph, non-linear. Then we draw our second line and it touches at x and f at x, and also at s plus dx and f at s plus ds, because the difference of one point to the other here is dx. So that's why the x, we had ds to it. Then the second vertical also go up. So, and also is dx, so it will be f at s plus dx. Now with this concept, we can find the slope formula. So we know a slope formula from college algebra is y, the difference of y and the difference of x. So y2 minus y1, s2 minus s1, if it's linear. Now remember y2 from our graph is f at s plus dx. y1 will be f at x. So we find the difference of f at s plus dx minus f at x, and also s plus ds minus x. And that gives us here. At the denominator, we can see that s plus ds minus x, the s's will cancel. So we get f at s plus ds minus f at s dx. So now we say that the right side of this equation is called the difference quotient. And the denominator ds is the change in x. And also the numerator is the change in y. Like y2 minus y1, s2 minus s1, the denominator. So here we can see we have s plus dx, f at s plus ds, which is our y section. So we call dy, and then dx. And the same concept here, it can be as small as possible. We still have two points. So we get f at s and new s plus ds and f at s plus ds. Here we say as the s approaches 0, what will happen? The second line approaches the tangent line. So we can see it's decreasing, it's approaching 0. And here we can see the second line now become a tangent. A tangent line means the line intersects the graph only once. Then we say the line is tangent to the graph. If it intersects twice, we say second line. So this will lead us to the definition of the slope of a graph using the limit process. So here we say using the limit process, you can find the exact slope of the tangent line at f, at x and x, which is also the slope of the graph of f at x and f at x. So to find the slope m of the graph of f at the point x and f at x is equal to the slope of the tangent line to the graph of f at x and f at x, which is our point, and is given by m equal to the limit ds approaches 0, m second. Then we have limit ds approaches 0, f at dx, f at s plus ds minus f at s over dx. Now, this is the formula we can use to find the derivative of any function. The only thing is that it's a long process because we have to simplify. And this will lead us to finding the formulas for derivatives like the sum rules, power rule, quotient rule, product rule. So let's see the example here. Here they say find a formula for the slope of a graph of f at x equal to s squared plus 1. Then after you find the formula finish, use that formula to find the slope at the point -1 and 2, which means when s is -1, y is 2. And then the second point, when s is 2, y is 5. So let's start. We use the m second, f at s plus ds minus f at s dx. That's the formula now. But now, anywhere we see f at s plus dx, we have, anywhere we see s, we have to substitute with s squared plus 1. Anywhere we see f at x. So this is what will happen. We have f at x dx. Here is s squared. So now this becomes s plus dx all square. And that's what we have here. Plus this is a constant value, so plus 1. F at s, nothing changes, so the same f at x, so to be s squared plus 1. Then we can simplify this equation. We open the square bracket here, so we have s squared plus 2s dx plus ds square using the perfect square formula plus 1. Then this is minus, so s squared plus 1 will change to minus. So we have minus s squared minus 1 divided by dx. S squared positive will cancel minus s squared. Plus 1 will cancel minus 1. And that's it. So let's see the next step. So we have 2s dx plus ds squared over dx. Now we know ds is common at the numerator, so we bring the ds out and remaining 2x plus 1 more ds because it's ds squared, so remaining 1 more dx. So we can see here we cancel ds, so we get what? 2x plus ds. We know ds is approaching 0, so the answer will be 2x. So now with the concept here, we can find the slope using this. So this is our formula now. X approaches, ds approaches 0. And remember they gave us the point. So using the formula m equal to 2s, you can find the slope at any point. So if the point given to us is -1, and 2 means s is -1. So we substitute 2s, it will be 2 times -1. The second point is 2 and 5, so which means s is 2 now. So 2 times 2. So when s is -1 and y is 2, the slope will be -2. And we can see from the graph, you can see that it's decreasing. Tangent line, the graph is decreasing. So it's negative value for the slope. Now, on our right side, it's increasing. So we get +4. So next is the derivative of a function. Now we know the limit process. We can use it for now to solve any derivative problems. So for example, here they give us a function f at x equal to s squared plus 1. And they say we should find the derivative of this function. Now, if we know the formula, the power rule, the answer will be 2x because derivative of a constant value is 0. So here we say when we use the limit process, this is the same example as previously. When we use the limit process, what did we get? We get m equal to 2x. So that would be the answer, the derivative of this function using the limit process. We get 2x. So that's the definition of derivative. And the derivative take f prime at x is equal to limit ds approaches 0, f at s plus ds minus f at x divided by dx. With this formula, I can find the derivative of any function. The only problem is it's a long process, so you have to simplify the expressions. Now, in this course, there are many ways we can represent a derivative of a function. So if they say we should find a derivative of a function, we can make it f prime at x, or we can make it y prime, or we can use the symbol dx dy, or we can say d f at s divided by dx. So find the derivative of y with respect to t for the function. Here we use the limit process. So if it's y, I'm going to look for dy dt because with respect to t. So dy dt will give me limit dt approaches 0, f at t plus dt minus f at t divided by dt. Now, when we look at this equation, it's the same as writing y equal to 2 times t to the power -1. So we're going to substitute. Anywhere we see f at t plus dt, we know y is 2 over t. So this will give me everything. It will give me 2 over t plus dt because it's including dt. But f at t is the same as 2 over t. So we have 2 over t, then 2 over t plus dt. Then we can simplify the equation, combine the two fraction difference together. And this is what we have. And next we can remove the parentheses. And here we can say, okay, dt approaches 0. What will happen here? Everything here will be 0. So we can say simplify first. Dt is here. We have the t also here, so we can cancel the 2. And then we have this now. The t approaches 0, so that will be 0 here. So later we get minus 2t times t, and that will give us minus 2 over t squared, and that will be our final answer. So the derivative of the function will be this. Now, before we go, in our next lectures, we're going to start with the derivative formulas. Now, if they say we should find the derivative of this equation, instead of following all this limit process and simplified expression, we can write it as 2t to the power -1. And this is a power rule. In a power rule, you subtract 1 from the exponent and you multiply the value of the exponent with the equation. So if I have 2t to the power -1, it will be t to the power -1, -1 times -1. So our answer will be 2 times -1, t to the power -2. So the answer will be -2 t to the power -2, which is the same as saying -2 over t squared. And that's what we get here. But instead of using all this limit process, very long process, we just use the formula power rule. So that will be our next lectures. Right now, we know what is a derivative, how we find the derivative of a function using the limit process. Now, in the next lectures, we are starting to use the derivative formulas. So again, wish everybody the best and thank you.